Welcome back to the Biomechanics Remote Teaching Lab. Today we're going to go through angular impulse, angular momentum relationship. Now you should have already watched the video on the impulse momentum, and that is a linear relationship. In this video, we're going to talk about the same relationship, but from an angular world perspective. So we're going to start with the equation, sum of torques equals I alpha. That's our angular kinetic analysis equation. We add up all the torques acting about an axis of rotation, and that equals the product of moment of inertia and angular acceleration. Moment of inertia being the resistance to change angular motion, and angular acceleration being the rate of change of angular velocity. And just remember, I is sum of all mass particles squared. That's our equation. And alpha is delta omega over delta t. All right, so what I'm going to do is just substitute those equations for the parameters in here. Oh, actually, I'm just going to substitute here for alpha and put in delta omega over delta t. Then I'm just going to do some algebra, rearrange this equation. I'm going to move delta t from this side of the equation over to this side. I do that by multiplying this side by delta t. So if I put delta t here, then that would cancel my denominator. And whatever I do to this side of the equality sign, I have to do the same thing over here. So I have to multiply by delta t over here. And I end up with this equation: sum of all torques acting about an axis of rotation times how long those torques are being applied equals a change in I omega. So what's I omega? Well, let's put some names to these now. This side of the equation we refer to as angular impulse. Okay, this side of the equation we refer to change in this part right here, which is angular momentum. All right, but the important part right here is change. All right. Angular impulse causes a change in angular momentum. Angular momentum by itself is just the product of moment of inertia and angular velocity. Okay, that's the equation for angular momentum. This equation states if we add up all the torques acting about an axis of rotation, and we know how long those torques are being applied, we'll understand how angular momentum is changed. Okay, let's keep looking at it. The definition for angular impulse, it's just a math definition, product of torque and time, or it's how long torques are being applied. And the definition of angular momentum is not a great definition, but quantity of angular motion. Okay, quantity of angular motion. Those are the word definitions for each of those. So let's look at them a little bit more, and let's start by doing a unit analysis. So let's check our units for each of these parameters. T delta t, angular impulse, will be the units of Newton meters, torque, times seconds, delta t. So let me just write that above here. Torque and delta t units. So we combine those because we're taking the product here. That's a delta. And we get Newton meter seconds. So these are our units for angular impulse. Let's look at the other side of the equality sign, and we have I omega. Remember, angular momentum is just this equation. I don't put the delta here because that delta is part of the angular impulse, angular momentum relationship. Right now, I'm just going to talk about angular momentum, the product of moment of inertia times angular velocity. I wrote down the equation for moment of inertia earlier. That's the sum of mr squared. And so those units for moment of inertia are kilogram meter squared. Angular velocity units have to be radians per second. Remember what I've said is anytime we use angular position, angular velocity, or angular acceleration, outside of just doing position, velocity, acceleration relationships, we have to use radians as our base unit for angular position, and therefore radians per second for angular velocity. Why? Because radians are unitless. They actually cancel out in this unit analysis check. So remember, radians are unitless. We calculate a radian, this angle between these two lines, by taking the ratio of how long this line is, how long that arc is, that secant, and how long the radius is. And so these are meter units over meter units, so length units over length units, so they're unitless. And we just call that a radian when we do that. All right, so in this development of these units over here, I actually drop out my radians, and I'm left with kilogram meter squared in the numerator and seconds in the denominator. So these are the units for angular momentum, and these are the units for angular impulse. All right, unique units, but they need to be the same units because they're on different sides of the equality sign in our angular momentum, angular impulse equation. All right, so let's look at that and just make sure that we've got the right units here. So we'll do a unit check. Here's our equation for the relationship between angular impulse and change in angular momentum. They have to be the same units because this equality sign is here. So here's angular impulse units. Here's angular momentum units that we just did. And I'm just going to draw this out a little bit more. Remember, a Newton, let me put a little sidebar over here. A Newton is a force, F equals ma, so that's kilogram meters per second squared as the base units. I'm just going to take those base units and substitute for n, kilogram meters per second squared, mass times acceleration, times meters times seconds. And I'm going to leave this side alone. Okay. Now, if I look at that, just looking at the algebra, I multiply m times m, so I get m squared. And then one of my s's in the numerator will cancel one of my s's in the denominator. And I'm left with kilogram meters squared per seconds, which is exactly the same as our angular momentum units. So everything checks out. That being said, it's more correct to say angular momentum units are Newton meter seconds, and it's more correct. Oh, sorry. It's more correct to say angular momentum units are kilogram meters squared per second, and it's more correct to say angular impulse units are Newton meter seconds. They're the same set of units, but it's just more correct to say these are the unit for angular momentum and these are the unit for angular impulse. Of course, you'll see textbooks to talk about angular momentum units as this and this angular impulse being units of this. That's fine. There's nothing wrong with that. But we'll try to distinguish between these sets of units just to minimize any confusion. Okay, so now let's try to talk about this in concept. What does this relationship tell us? And let's start with just the concept of angular impulse causing a change in angular momentum, quantity of angular motion. All right, here's our equation. I rewrote it here. Sum of delta t, sum of the torques acting about an axis of rotation times how long those torques are being applied causes a change in angular momentum. Let me just write that out a little differently. I'm leaving this part to be the same. The equal sign is here, final minus initial. So final angular momentum minus initial angular momentum. If we take the difference between those two, we get sum of torques equals, sum of torques times delta T. So this is the same relationship, just written out a little bit differently. Now this becomes really important. And let's look at a simple situation to try to explain this. Let me just write this out here. Final angular momentum minus initial angular momentum. Okay, this is going to be really important as we start looking at angular movements, this relationship, and it really gets us to understand movement strategies. But I want to start with a real simple or seemingly simple task, and you'll see how quickly this can get complicated. But let's start with sports that are considered aerial sports, like springboard diving or cliff diving, or ski jumping, skateboarding, where you're jumping off into the air, doing some type of trick, or trampoline type of work. Once you're off in the air is the time that I'm interested in, not when you're in contact with the ground or the diving board or anything. You have to be airborne, so you have to be in the air. So now I'll just draw a person doing a somersault in the air. So not touching the ground. And if we have this person rotating in the air, the person will actually rotate about the center of mass. So axis of rotation is center of mass. I'll just write that out so we have it. Center of mass, COM. It's the point where all mass seems to be concentrated. It is not a fixed point in the body. It changes. So if I move my arms up, my center of mass will move towards that mass. If I move the arms down, then the center mass would move down also. So it's just a point where all mass seems to be concentrated. When we throw an object in the air, it will rotate about the center of mass, okay? So now let's do a kinetic analysis. Let's identify all the forces acting on this object. And if we look at this, the forces acting on the object is simply the force of gravity, which is the weight of the object. Gravity is pulling down on the diver, or this could be a trampolinist or a skier or whatever, pulling downwards. And that force vector is acting at the center of mass of the person. So if the force is acting at the axis of rotation, we know that that force does not cause any torque. So if we just go back to our equation, so Fg is the acts at the axis of rotation, the force of gravity acts at the center of mass. Therefore, the torque due to the force vector of gravity is equal to the product of force gravity times its moment arm. I put a sub g in there. Because sub d perpendicular g is 0, because the force is acting at the axis of rotation, there's no torque generated. Okay, it's just like if you go and try to open a door, but you push right on the axis of rotation of the door, you can't open the door. You're not generating any torque, no tendency of this force to cause rotation. Okay, so this is an important point to understand here. No torque due to force, and therefore no external torques acting on the person, because there's no other pushing or pulling going on this person. No other forces, nothing else acting on the person. Yes, the body is creating forces inside the body, causing joints to move, and we're going to deal with that in just a second, but no external torques acting on the person. All right, so let's look at this a little bit further. We're going to continue with our kinetic analysis. Now we're going to be more specific and look at angular kinetics. Let's start with our equation. Sum of torques equals I alpha, or I'm going to use the more general relationship that we just dealt with. Angular impulse causes equals a change in angular momentum. And we have no torques. Therefore, the sum of torques times delta, therefore, sum of torques times delta t is 0. We have no angular impulse, okay? No angular impulse acting on the diver when the diver is in the air. Okay, it's really important. When person, I'll say person, I won't use diver yet because this could be anything. Person is in air. Okay, really important condition here. I'm not talking about when the person is pushing on the ground, on the diving board, or on a trampoline. It's when the person is in the air only. Because once the person's in contact with the ground, we have another force, the ground reaction force. And then we have to include that ground reaction force in this equation up here, ultimately. All right, so let's tease this out a little bit more. And therefore, the sum of the change in angular momentum will be 0 because of this relationship. If this side, if the left-hand side of this equality sign is 0, the right-hand side has to be 0 as well. And therefore, no change in angular momentum. There's no change in angular momentum when the person is in the air. Really important. Really, really, really important. Okay, when the person is in the air. But we know when we watch aerial maneuvers, when we watch people performing tricks in the air, we do see a change in angular velocity. So how does angular velocity change? I shouldn't have shown that first. How can angular velocity change? Well, angular velocity will change, and I'll show you this in a second, by manipulating the moment of inertia. Remember, this is not constant. This can change. Okay, let's look at that. And here I've redrawn my person in the air in 2 moments in time. I'll just put time 1 here and time 2 here. These are just 2 moments in time. Doesn't matter where they are. This could be the middle of the dive. This could be the end of the dive, whatever. Here's the center of mass. Center of mass. Remember, center of mass is axis of rotation. Axis of rotation. So in each of these situations, FG, I did a bad job of drawing where that center of mass is, but that's okay. FG, therefore, no torques acting about the axis of rotation, and therefore no angular impulse, and therefore no change in angular momentum. But let's look at how, if we just think about this person spinning in this position versus this position, just conceptually, you can envision that you can spin faster when you're tucked into a ball than when you're straight like this or laid out in this type of position. Well, let's look at moment of inertia here versus moment of inertia here. What's the relationship? Well, these are not the same. One of these is greater than the other. And if we think of our equation, sum of mass equals mr squared, the further the mass is from the axis of rotation, the greater the moment of inertia. So moment of inertia is greater for this position than this position. Well, now let's look at our equation. Sum of torques times delta t equals change in angular momentum. And I'm just going to write it here to give myself a little bit room. I'm going to separate this out here so I don't get this confused. I f omega f minus I omega I. So knowing that this change is going to be 0, okay, knowing that this is going to be changed, the difference between these 2 moments in time is going to be 0. Whatever the product is here has to equal the product here. Therefore, if the moment of inertia for time 1, the initial time, is less than the moment of inertia here, then angular velocity has to be greater here than here in order that the products are the same, because there's no change in angular momentum. So how does a diver spin faster? Why does a diver spin faster when in a small tucked position like this versus a straight position like this? The reason is moment of inertia is different, and this that's part of the reason. The other reason is the angular momentum is constant, it's conserved, and because moment of inertia is changing, that's going to change angular velocity. Okay, so I mean, if we really wanted to, we could put some numbers on here. Let me just leave this up here. I'll do, for example, e.g., if angular impulse is 0 Newton meter seconds, which is the situation we're dealing with, and if, let's just make up some fictitious numbers, if I omega 1 is 10 kilogram meters squared per second, and moment of inertia 2 is 20 kilogram meters squared per second, and if in the initial angular velocity is 10 radians per second, what's the final angular velocity? Will it be faster or slower? Well, I'm going to just jump back up to this equation right here. I'm not going to rewrite the whole thing here, but I'm going to use this equation, IF, so 20 kilogram meters squared per second times omega F, which we don't know, minus, I'll put brackets around that, minus the initial moment of inertia, times, I'm sorry. Let's see, I'm getting my units mixed up. Moment of inertia is only kilogram meter squared. Moment of inertia, kilogram meter squared. I'm only working on half a cup of coffee, so I better catch myself. Hopefully you caught me making that mistake. I guess I could edit it out, but I'm not going to, because we're all need to be okay with making mistakes. So moment of inertia, 10 kilogram meters squared. Moment of inertia 2, 20 kilogram meters squared. Initial angular velocity, 20 radians per second. And we have our equation 20 kilogram meters squared times final angular velocity minus moment of inertia initial times the initial angular velocity, which is 10 radians per second. So my product over here has to be 100 kilogram meters squared per second. Therefore, I need to make this 100 in order that this is all equal to 0, because we have no external torques acting on the system. We have the constant angular momentum and no angular impulse. So 20 times what is going to give me 100? So 20 times 5, and we're still radians per second, is going to be 100 minus 100 will make this equality sign true. 5 radians per second, whereas initially it was 10 radians per second. Initially it was 10 radians per second, so it slowed down. So the person slowed down in rotation. The person's rotating slower here than initially. So the person slowed down. How did the person slow down with no angular impulse? They changed moment of inertia. They increased moment of inertia. And you know this, and in fact, I'll post another video of watching a diver change angular velocity by changing his or her moment of inertia. Moment of inertia increases, angular velocity is going to slow down. If moment of inertia decreases, angular velocity will speed up once the person is airborne. Okay, so that is the angular impulse angular momentum relationship, and it helps us understand how angular velocity changes during an aerial maneuver. Now, this has been a simple task. What I'll also do is I'll post a video of a more complex task where rotations may occur around multiple axes. And that's sort of fun to go with. But for our purpose, we just want to start with understanding rotation about a single axis. Okay, thanks everybody.